One factory, 40 acres of machinery, zero sunlight required inside the building. And yet, this single building can produce enough solar panels every year to power a mid-sized city for a decade. Here's the strange part. The company that owns this factory might never install a single panel on a rooftop. So how does a business that never touches sunlight become one of the most fought-over industries on the planet? The answer involves razor-thin margins, billion-dollar subsidies, and a supply chain that runs through exactly one country. Stick around. By the end of this video, you'll understand exactly how the money moves and why most people get this business completely wrong. Today, we're breaking down the real economics behind owning a solar panel manufacturing plant, not the marketing version, the version with actual numbers. We'll look at how these factories actually make money, what it costs to run one, and why the barrier to entry is higher than almost any other manufacturing business you could start. You'll see why a factory that looks profitable on paper can go bankrupt in 18 months. And you'll understand why governments are now throwing tens of billions of dollars at companies just to convince them to build here instead of somewhere else. This is an industry where physics, politics, and spreadsheets collide. Let's get into it. A solar panel factory makes money in a way that's deceptively simple to describe and brutally hard to execute. It buys raw materials, polysilicon, glass, aluminum framing, copper wiring, and it sells a finished, tested, warranted panel for more than the sum of those parts. That gap between input cost and output price is called the conversion margin, and in this industry, it is razor thin. On a standard 400-watt residential panel, a factory might spend somewhere around $90 to $110 in materials and processing, and sell that same panel for $120 to $150, depending on the year and the market. That is not a typo. We are talking about margins that, on paper, look more like a grocery store than a tech company. The real revenue engine isn't the panel price, it's volume. A mid-sized factory producing 2 gigawatts of panel capacity per year, which is a fairly standard scale in this industry, might ship somewhere in the range of 4 to 5 million individual panels annually. Multiply a thin per unit margin by millions of units, and suddenly a company that looks unprofitable per panel is generating hundreds of millions of dollars in gross revenue. But panel sales are only one revenue stream. There are others that matter just as much. Long-term supply contracts are the backbone of serious factories. Utility companies building large solar farms don't want to negotiate panel purchases one truck at a time. They sign multi-year offtake agreements, sometimes locking in 5, 7, even 10 years of guaranteed panel purchases at a pre-negotiated price. This is where the real stability comes from. A single utility-scale contract can represent more revenue than an entire year of scattered residential sales. Then there's the byproduct and technology licensing side, which most people never think about. Factories that develop more efficient cell technology, squeezing out even half a percentage point of additional energy conversion, can license that technology to other manufacturers for royalty payments. In an industry chasing efficiency gains measured in fractions of a percent, that half a point can be worth tens of millions of dollars in licensing revenue over a patent's lifetime. Finally, there's the government incentive layer, which in recent years has become one of the largest revenue contributors of all. Programs like production tax credits pay manufacturers directly for every watt of solar capacity they produce domestically, regardless of who buys the panel. In some cases, this credit alone can add several cents per watt in pure profit, stacked on top of whatever the panel actually sells for. For a factory producing 2 gigawatts a year, a credit of just 3 cents per watt translates into roughly $60 million of additional annual revenue that has nothing to do with the customer at all. So when you add it up, panel sales, offtake contracts, licensing, and government credits, you start to see why this industry, despite thin unit margins, can still be enormously lucrative at scale. Catch, as we're about to see, is that scale itself is brutally expensive to reach and even harder to maintain. Owning a solar panel factory is not like owning a warehouse with some machines in it. It is one of the most capital-intensive operations in modern manufacturing. Let's start with the single biggest recurring cost, polysilicon. Polysilicon is the refined material that becomes the actual solar cell, and its price is notoriously volatile. In a calm year, polysilicon might cost around $8 to $10 per kilogram. During a supply crunch, that same kilogram has spiked past $30. For a factory that consumes thousands of tons of polysilicon annually, that kind of swing can turn a profitable quarter into a loss-making one without a single operational mistake being made. Next comes energy. This is the part most people underestimate entirely. Producing polysilicon and processing raw silicon into wafers requires furnaces running at extremely high temperatures, essentially around the clock. A single large facility can consume as much electricity as a small city. Energy costs alone can represent somewhere between 15 and and 25% of total production cost, depending on the region and its electricity prices. This is actually one of the biggest reasons manufacturing has clustered so heavily in specific regions. Cheap, reliable, industrial-scale electricity is not optional. It's existential. Then there's labor and skilled technical staff. Modern solar factories are heavily automated, but automation doesn't eliminate labor cost. It shifts it. Instead of hundreds of assembly workers, a factory needs dozens of highly trained engineers and technicians who can operate, calibrate, and repair multi-million-dollar equipment. These roles command significant salaries, and a shortage of qualified technicians in a given region can delay production ramp-up by months. Equipment maintenance is another quiet cost center. The machinery used to cut, dope, and coat silicon wafers is precision equipment, often imported, and often requiring specialized parts that aren't sitting on a shelf nearby. A single critical machine going down for even 2 weeks, waiting on a replacement part shipped internationally, can cost a factory millions in lost production. Quality control and testing add further cost. Every panel needs to be tested for output consistency, durability, and defect rates before it can carry a warranty. And warranties in this industry typically run 25 years. That is not a marketing promise. It's a legal and financial commitment the factory is making today about a product that needs to keep performing for a quarter of a century. Building a reserve fund or insurance structure to back that warranty is itself a cost most outside observers never even consider. Finally, there's regulatory compliance and environmental handling. Silicon processing generates hazardous byproducts, and disposing of them safely and legally is neither cheap nor optional. Environmental permitting alone can take a year or more before a single panel is produced, and compliance failures can result in fines large enough to threaten the entire operation. When you stack polysilicon volatility, industrial-scale energy, skilled labor, equipment maintenance, quality assurance, and environmental compliance on top of each other, the picture becomes clear. This is not a business where you can start lean and scale up carefully. The cost structure demands scale from day one, which brings us to the next problem. Let's talk about what it actually costs to open the doors on a facility like this, because this is where most people's assumptions completely fall apart. A gigawatt-scale solar panel manufacturing plant, a serious, competitive facility, typically requires somewhere between $300 million and $1 billion in upfront capital investment, depending on the level of vertical integration. That figure isn't just the building. It includes land acquisition, specialized manufacturing equipment imported from a small handful of global suppliers, cleanroom construction, electrical infrastructure upgrades, and the permitting process itself. The equipment alone is staggering. Wafer cutting machines, diffusion furnaces, and automated stringing equipment for assembling cells into panels can each cost anywhere from several $100,000 to several $1 million per unit, and a functioning production line needs dozens of these machines working in sequence. Now here's where it gets interesting. The decision that matters most before construction even begins is how vertically integrated the factory will be. A company can choose to only assemble finished panels from purchased cells, a lower cost, lower barrier entry point. Or it can choose to produce its own wafers and cells from raw polysilicon, a dramatically more expensive but far more profitable long-term structure because it controls more of the value chain and isn't exposed to a supplier's pricing whims. Fully integrated facilities can push total investment well past the billion-dollar mark, but they also capture margin at every stage of production instead of just the final assembly step. This is the same logic that separates a company that merely bottles soda from one that owns the syrup formula, the bottling plant, and the distribution trucks. Beyond the factory itself, there's the working capital requirement, the cash needed simply to keep operations running while waiting for customers to pay. Raw materials must be purchased months in advance. Panels take time to manufacture, test, and ship. Payment terms with major utility customers can stretch 60 to 90 days after delivery. For a factory running at full capacity, working capital needs alone can require tens of millions of dollars sitting in reserve, simply to bridge that gap. Then there's the timeline risk baked into this investment. From breaking ground to full production capacity, a new facility typically takes 18 to 30 months. During that entire window, the company is spending enormous sums with zero product revenue coming in, betting that market prices, government incentives, and demand will still look favorable by the time the factory is finally operational. This is precisely why solar manufacturing has historically been dominated by a small number of very large, very well-capitalized players, and why new entrants without deep-pocketed backers or government support rarely survive the first few years. The barrier isn't creativity or work ethic, it's raw capital, patient investors, and the ability to absorb 2 to 3 years of spending before seeing a return. Here's something that surprises most people learning about this industry for the first time. The vast majority of the world's polysilicon refining capacity is concentrated overwhelmingly in one country. Industry estimates over the past several years have placed that country's share of global polysilicon production somewhere above 75 to 80%. That concentration didn't happen by accident. It happened through sustained, aggressive state-backed investment in manufacturing capacity rapidly over more than a decade, driving global prices down to a level that made competing anywhere else extremely difficult. For any factory owner outside that country, this creates a permanent strategic vulnerability. Your single most important raw material, the one your entire product depends on, is controlled by a small number of overseas suppliers. When trade tensions rise, tariffs shift, or export restrictions tighten, factory owners outside that dominant region can see their input costs jump overnight, sometimes by 20, 30, even 50% without warning. This is exactly why governments in North America, Europe, and parts of Asia have started pouring public money into building alternative polysilicon and cell manufacturing capacity from scratch. It isn't purely an economic decision. It's treated as a matter of energy security, on the same level as domestic oil refining or semiconductor production. But building an alternative supply chain from zero is enormously expensive, and it takes years to reach cost competitiveness with an established, subsidized incumbent. In the meantime, factory owners are forced into a difficult balancing act, paying more for domestically or regionally sourced materials to reduce geopolitical risk, or accepting cheaper imported materials and living with the exposure. Some manufacturers hedge by signing long-term supply contracts locked at fixed prices, insulating themselves from short-term volatility in exchange for slightly higher baseline costs. Others diversify their supplier base across multiple countries, sacrificing some economies of scale in exchange for reduced dependency on any single source. Neither option is free. Both represent a direct cost of doing business in an industry where the core input is a geopolitical chess piece as much as it is a commodity. This is the layer of the business that spreadsheets alone can't capture. A factory can have flawless operational execution and still get blindsided by a trade policy decision made on the other side of the planet. Almost no solar panel factory today operates purely on free market economics. Government policy is baked into the business model at nearly every level. Production tax credits, which we touched on earlier, pay manufacturers a set amount for every watt of capacity they produce domestically. In some major markets, these credits have been generous enough to single-handedly determine whether a new factory project gets approved by investors or shelved indefinitely. Investment tax credits work differently, offsetting a percentage of the upfront capital cost of building the facility itself, effectively reducing that daunting billion-dollar price tag we discussed earlier. Import tariffs are the flip side of this coin. Many countries impose tariffs on panels manufactured overseas, specifically to make domestically produced panels more price competitive. This can dramatically shift where it makes financial sense to build a factory in the first place, sometimes overnight, when new tariff legislation passes. A factory owner deciding where to build isn't just asking, where is labor cheap or where is energy affordable? They're asking, which government is currently paying the most to have this factory built on their soil? This has led to something close to a bidding war between regions and countries, each offering tax abatements, direct grants, low-interest loans, and expedited permitting to attract major manufacturing investment. Some of these packages have reportedly reached into the hundreds of millions, and in select megaprojects, over $1 billion in combined incentives for a single facility. But here's where it gets interesting, and where a lot of investors get burned. Subsidies are political, which means they are not permanent. A change in government, a shift in budget priorities, or a renegotiated trade agreement can alter or eliminate incentive programs with relatively short notice. A factory whose profitability model was built assuming a certain tax credit would exist for 10 years can find itself in serious financial trouble if that credit is reduced or removed after only 3 or 4. This is why sophisticated operators build financial models with multiple subsidy scenarios, best case, base case, and a policy withdrawn worst case before ever breaking ground. Ignoring that worst case scenario has been the downfall of more than a few ambitious solar manufacturing projects over the past 2 decades, some of which secured massive initial funding only to collapse when policy support shifted beneath them. Beyond supply chains and subsidies, there's a broader set of risks that make this one of the more volatile manufacturing industries to operate in. The first is price collapse from overcapacity. Because so many governments and companies have raced to build solar manufacturing capacity simultaneously, the industry has repeatedly experienced periods where global production capacity vastly exceeds actual demand. When that happens, panel prices can crash by 30, 40, even 50% within a single year, as manufacturers compete desperately to sell inventory rather than let it sit in warehouses depreciating. Factories that built their financial projections around a certain panel price can suddenly find themselves selling below production cost just to maintain cash flow and keep workers employed. This boom and bust cycle has already claimed a significant number of manufacturers over the past 15 years. Companies that looked financially unstoppable during a price boom have gone bankrupt within 18 months of a price crash. The second major risk is technology obsolescence. Solar cell efficiency has been improving steadily for decades, and a factory built around one generation of cell technology can become uncompetitive within just a handful of years if it fails to reinvest in upgrades. Retrofitting a production line for a new cell architecture isn't a minor tune-up. It can require tens of millions of dollars in new equipment and months of production downtime. A factory owner who delays that reinvestment risks watching competitors' higher efficiency panels win contract after contract simply because they generate more electricity per square foot of installed space. The third risk is customer concentration. Because so much revenue flows through a relatively small number of massive offtake contracts with utilities and large developers, losing even one major customer can create a serious revenue gap. Unlike a consumer retail business with millions of small transactions spreading out risk, a manufacturing plant might have 3, 4, or 5 customers responsible for the majority of its annual revenue. If one of those customers delays a project, renegotiates pricing, or switches suppliers, the impact on the factory's finances can be immediate and severe. Finally, there's currency and interest rate risk. Because these factories require such enormous upfront capital, most are financed heavily with debt. Rising interest rates directly increase the cost of servicing that debt, squeezing already thin margins even further, and can make previously profitable projects unviable before they're even finished being built. For any factory operating internationally, currency fluctuations between where materials are purchased and where panels are sold can add another layer of financial unpredictability on top of everything else. Together, these risks explain why solar manufacturing has one of the higher failure rates among industrial businesses, despite operating in a sector widely described as the future of energy. The future being real does not automatically make any individual company's balance sheet safe. Despite everything we've just covered, this remains one of the fastest growing manufacturing sectors on the planet, and understanding how successful players actually scale reveals a lot about where the real money gets made. The first path to scale is straightforward capacity expansion. A factory operating profitably at 1 gigawatt of annual output can often expand to 2, 3, or even 4 gigawatts by adding production lines within the same facility, spreading fixed costs like management, land, and administrative overhead across a much larger production volume. This is where economies of scale genuinely kick in. Doubling production capacity rarely doubles overhead cost, which means unit margins can improve meaningfully as a factory grows, assuming demand keeps pace. The second path is deeper vertical integration, which we touched on earlier. A company that starts as a panel assembler can gradually move upstream, acquiring or building its own wafer and cell production, and eventually its own polysilicon refining capacity. Each stage of integration captures margin that would otherwise go to an outside supplier, and it insulates the company from the exact supply chain volatility we discussed earlier. The third path is geographic diversification. Building factories across multiple countries or regions allows a company to serve local markets directly, avoid import tariffs, tap into region-specific subsidy programs, and reduce its exposure to any single country's policy shifts. This strategy is expensive and slow, but it's increasingly how the largest players in the industry are structuring themselves, treating manufacturing capacity almost like a hedged investment portfolio spread across multiple political jurisdictions. The fourth path, and arguably the most overlooked, is downstream expansion into project development and energy sales. Instead of simply selling panels to a utility, some manufacturers have begun developing and even operating their own solar farms, selling electricity directly rather than just the hardware that generates it. This shifts the business model from a low-margin manufacturing operation into a long-term, recurring revenue energy business, one that behaves financially much more like a utility company than a factory, with predictable decades-long cash flows instead of cyclical panel price swings. Companies that successfully make this shift often trade some short-term manufacturing margin for long-term earning stability, smoothing out the boom-and-bust cycle that plagues pure-play manufacturers. It's worth noting that scale itself becomes a competitive weapon in this industry in a way that's more extreme than in most other manufacturing sectors. Larger factories can negotiate better raw material pricing, absorb short-term price crashes more easily than smaller competitors, and qualify for larger government incentive packages that are often explicitly tied to job creation and production volume thresholds. This creates a self-reinforcing cycle where the biggest players keep getting structural advantages that smaller, newer entrants simply cannot match, one of the clearest examples in modern manufacturing of scale compounding on itself. Let's put some of these figures side by side, using industry-wide estimates, to get a clearer sense of scale. A gigawatt-scale solar panel factory, fully built and operational, might represent somewhere between $300 million and $1 billion of total capital investment, as we discussed earlier. For comparison, that is roughly in the same range as building a mid-sized semiconductor packaging plant, though dramatically less than a leading-edge chip fabrication facility, which can run into the tens of billions. On the revenue side, that same gigawatt-scale facility, operating at full capacity and selling into a healthy market, might generate somewhere in the range of $400 to $600 million in annual gross revenue before accounting for the cost of materials, labor, and overhead we detailed earlier. After the true cost of goods sold, polysilicon, glass, aluminum, labor, energy, and equipment depreciation, net margins in a strong year for the industry industry have historically landed somewhere in the range of 8 to 15%, though in oversupply years, that figure can shrink to near zero or turn negative entirely. Compare that to a well-run semiconductor fabrication business, which in strong years can post net margins well above 25 to 30%, largely because of far higher barriers to entry and less commoditized pricing.
Or compare it to a typical grocery retail chain, which often operates on net margins closer to 2 to 4%, illustrating just how much volume and government support matter in an industry like solar manufacturing, where margins sit somewhere in between heavy industry and thin margin retail. On the employment side, a large-scale solar factory might employ somewhere between 1,500 and 3,000 workers directly, spanning production line operators, engineers, quality control staff, logistics coordinators, and administrative teams. Indirect employment, suppliers, logistics companies, and local service businesses supporting the facility can add several thousand more jobs to the surrounding regional economy, which is precisely why governments treat these projects as major economic development wins worth billions in subsidy packages. Finally, consider payback period. A well-capitalized, well-managed facility benefiting from favorable subsidies and stable demand might reach positive cumulative cash flow, meaning it has fully recovered its initial billion-dollar investment, somewhere in the 6 to 10-year range. A facility that gets caught in an oversupply price crash during its early years, however, can see that payback periods stretch well beyond a decade, or in the worst cases, never fully materialize before the technology itself becomes outdated and requires reinvestment. This is the central tension of the entire industry, expressed in a single number. The difference between a 7-year payback and a 15-year payback often comes down not to operational excellence, but to the timing of when a factory happened to be built relative to the industry's boom and bust cycle. So what should you actually take away from all of this? Owning the solar panel factory looks, from the outside, like a straightforward bet on an industry with obvious long-term tailwinds. Global demand for solar energy is rising, and it's rising for decades to come. But the lesson underneath all of it is this: being right about the long-term trend does not protect you from short-term economics. Thin margins, capital intensity, supply chain concentration, and policy dependency can sink even a company operating in a genuinely growing market. This principle extends far beyond solar manufacturing. Any investor, entrepreneur, or business owner should ask the same core questions before committing capital to a capital-intensive, subsidy-dependent, or supply chain concentrated business. How exposed am I to a single input, a single customer, or a single policy decision? The businesses that survive long enough to benefit from a rising tide are rarely the ones that grew fastest. They're the ones that built in enough of a buffer to survive the years when the tide went out. In one sentence, solar panel manufacturing is a capital-intensive, subsidy-driven business where the winners aren't the fastest movers. They're the ones who can survive the industry's brutal boom and bust cycles. If this kind of breakdown helped you understand how a real industry actually makes money, hit subscribe. We break down a different business model like this every single week. Next time, we're going inside a completely different kind of empire: the hidden economics of owning a shopping mall, and why some of the biggest retail collapses in history left their landlords richer, not poorer. See you in the next one.